Problem 59. Page 247. Here we have a 20 kilogram block. Let's say we have block A. And here we have block B. A is connected to B by a light string here, passes through a massless pulley and a frictionless pulley. It means the tension here equals to the tension here. Okay, the block B is connected to a massless spring with K equals to 250. The spring at this position has a equilibrium position. Okay, at this level we have X equals to O. We don't have compression, we don't have extension, nothing. It's the equilibrium position. We push here, the block A is pulled 20 centimeter down the inclined plane. Before, the inclined plane has no friction, mu equals to O. Okay, we pull A down 20 centimeter on the inclined plane. I push this system down 20 centimeter. So in this case, B will be pulled up 20 centimeter. So here we get, let's say here we have A, and here we have B. And I release the system from this point. When I release the system, A will move up and B will move down. When B arrives to this position again with a velocity VB, I need to calculate VB. VB here is at 20 centimeter from the floor. Okay, this is the problem. Okay, so here we have 20 centimeter. I push the system down. When I push the system down 20 centimeter, and here we have inextensible string, A or B will be up at 20 centimeter. Okay, so here we have the same value, 20 centimeter. Let's say the block A and B initially at this point. We have orange here. Okay, this is A. Okay, and here we have B. Okay, initial system, at the initial system, A is here. This is the position initial of A, and this is the position initial of B. When A moves up and B moves down, we get the final position of A and B. Here we have final position of A, and here we have final position of B. Okay, so we have initial system and final system. A and initial and final A here, and initial and final B is here. First of all, we have a isolated system. So here we can say in general, delta mechanical energy equals to delta kinetic plus delta potential. We can say delta potential G plus delta potential E, okay, equals to omega F in general case. When we have a motion from initial to final, as you see in the total system here, we don't have F, which is equal to mu times n. We don't have a mu. So here we have a conservation of mechanical energy. We can say here that omega F equals to O. F equals to O. We don't have friction. So we have a conservation of mechanical energy. If we have here a mu, you have to say omega F, and we calculate omega F. Okay. Initial mechanical energy, here we have initial kinetic of the system plus initial potential G plus initial potential elastic initial equals to final kinetic, final potential, gravitational potential energy, and also we have a final elastic. Let me explain a very important point. When the block B is here, you know the spring is attached to the block. So here we have an expansion. In this case, we have an expansion with x equals to 20. When I push this object 20 centimeter down, here we have an expansion of the spring with x equals to 20 centimeter. They are attached. Okay, it's very important here. And you know, here we have x equals to O. Okay. Let me continue. Here, about the kinetic energy. You know, the initial system. Initially, about the block A. Before, let me put x and y for each block. You know, here we have two dimensions. We have this system and we have this system. We have to put the x-axis, y-axis for each block independently. Okay? So here we have the minimum position and the maximum position. Let's say between this point and this point. Here we have 20 centimeter. Let me draw well, 20 centimeter between here to here. Okay, 20 centimeter. Okay, this is the lowest level. and this is the highest level. Okay, and the distance between A from this point to this point equals to 20 centimeter. For this A, for this block, I take the reference at the lowest point. Here we have OX. O, X, Y. Okay, you choose the lowest point. And for the block B, I take X and Y at the, we can take here and we can take here. Okay, we get the same result. Okay, let me take X and Y here, the reference. I said this before, for this kind of system, you have to choose X and Y, the reference, independent for A and B. Okay, initially we don't have velocity. A and B at the initial position has V equals to O. Let me see before. We have a inextensible string. So VA equals to VB at any point. Okay. So VA equals to VB at any point. Initially, we don't have velocity. So VA equals to VB equal to 0. So we don't have initial kinetic. Let me write here. The kinetic energy initial for A equals to O and for B equals to O. Okay? You have to calculate for all the system. Okay. Let's talk about the gravitational potential energy. Equals. For A is at a height equal to 0. We don't have height. Here we have x-axis. We don't have height. 0. For B, B is at this position from the x-axis. This is the height of B initially. Here we have 20 plus 20. We have 40. So plus m of B, G times 40 centimeter times 10 minus 2 to get 40 times 10 minus 2 meter. This is about the gravitational potential energy. Let's talk about the elastic potential energy. Initial. At the initial state, the spring is here. Okay? Is attached from here to here. So here we have x from here to here. X equals to 20 in this case. You know, 20 is here. So we can write the initial potential elastic equals to K over 2 times x squared equals to 20 times 10 minus 2 square. Okay, this is about the initial state. Let me take the final state. The final state, the system moves down So B will be here, and A moves up. A will be here. Sure, A has a velocity VA, and B has a velocity VB. Okay, it's clear now. Don't forget the initial axis, the initial position. It was here. Let's say here. And the distance from here to here equals to 20. Okay, so the block as the final state has a height, this height. This one is HA as the final state. And B has a height equals to 20 centimeter at the final position. Okay, so we can write, this is initial, we can write the final. The kinetic final of the system equals, here we have VA and VB. You know VA equals to VB. We can write have mv square of A plus mb over 2v square. This is the kinetic total of the system. The gravitational potential energy final of the system. You know here, A as the final state is at a height HA. We have to calculate HA. You know, this angle is 40. You have two parallel lines. This angle must be 40. To calculate HA, we can say sine 40 equals to HA divided by 20 centimeter divided by 0.2. So we can calculate HA equals to 0.2 sine 40. Okay, so A is at mg HA plus B, I took the x-axis here, is at 20 centimeter. So we have MB times G times HB. Here we have HB. This one is HB. Okay, about the elastic potential energy final. As you know, at this position here, we don't have x. X equals to O. So have kx squared equals to O. We substitute the value, each one. Okay, first of all, we add this value equals to this value. We can write 0 kinetic energy initial plus mb g times 40 times 10 minus 2. Okay, it's better to put here the x-axis. In this case, the final height equals to O. Anyway, plus the elastic potential energy equals to K k equals to 250 divided by 2 x squared equals to 0.2 square. It's all about the final, the initial state. Finally, what we have, kinetic final equals to v square over 2 ma plus mb. We can add these values plus, let me, okay, plus this one, m a g h a plus mb g hp. Okay, let me substitute the value, all the values here. Here we have v square over 2, ma equals to 20, mb equals to 30, ma times g, ha equals to 0.2 sine 40. Okay, ha plus mb equals to 30 plus 9.8 plus hp equals to 0.2. We have all the values. We can put here mb equals to 30. We can calculate here v, the value of v. I give you the answer. Is the problem the value v equals to 1.24 m per second. Okay, this is the answer. That's all about this problem. Just if you have mu, in this case, you have to use this relation. Okay, just you have to add omega f equals to minus mu times n times d equals to 20, and you can solve with the same procedure. Okay.